All right, so what we're doing in these problems are maximizing or minimizing something. So here is sort of the gist of it. If you were given a piece of rectangular paper like this, and you were to form a rectangular box from it by removing 4 corners, obviously of equal length for each corner. And then when you fold up the edges, you know, if you take the time and measure it carefully, you go like this. Okay? And then when you fold up the edges like this, you would get a rectangular box. The point is, where would you cut in the corner so that when you fold it up, you would get the biggest volume? So that's what we're doing in all of these applications, is that we are either maximizing something or minimizing something. We've been doing it, but with functions just called f, or maybe s of t, or x of t. They didn't really have any geometric meaning yet as formulas. So for example, just listen. If I wanted to find where f had a maximum or a minimum, that means absolute, not local. What were the steps I took? I took the derivative. I had set it equal to what? 0. That's right. I got my critical numbers. If the extreme value theorem applied, then I made a chart, took the endpoints of the domain, if it was continuous on a closed interval, took the endpoints, took the critical points that fell within that interval, found the y's, the biggest is the max, the smallest is the what? Or I could have shown by a number line test on f prime that the derivative changes exactly how many signs? Once. Either from positive to negative or what? Negative to positive. If that alternates at all or changes signs more than once, the number line method would not work. Agreed? So what we're back at is the same thing, but these functions are not necessarily like what we've had before. They're a little different, involving area and volume and so forth. Okay? So let's look at the first example on your handout. It says here, in the summer, the activity level of a certain type of lizard varies according to the time of day. A biologist has determined that the activity level is given by the function, let's write it out, a at t equals 0.01 t cubed minus 0.315 t squared plus 2.04 t plus 5, where t is the number of hours after 12 noon. For what value of t is the activity level the highest? For what value of t is the activity level the highest? So if this determines the activity level of the lizard, then this is what we want to maximize. We want to maximize a at t, which means we need to take its what? So a prime at t, by hand, dropping that down, we'll get 0.03 t squared minus what do I get next? What?
0.63 t.
Yeah, 0.63 t plus 2.04, correct? And there's my derivative. We're not going to factor that. So what I would do is put this in y1. I'm not going to have time to do that now with you. Well, we can do it quickly. Let's do that, because we need to know that by now. So let's go to y1. And we're going to enter in y1, 0.03 x squared minus 0.63 x plus 2.04. And just make sure that's the only one highlighted. You're on a window from 0 to 12 only. So go to window, max, the minimum is 0 for x, and the max is 12. And we're me that when we graph the derivative, we only see one sign change. Remember, we're graphing the derivative. We took it by hand. And do I have only one sign change from 0 to 12?
Yeah.
And we can hit second, calculate 2 for 0, cursor to the left bound of it, so that it's a positive side, or a positive y. Cursor to the right, so it becomes a negative y value. And then on top. So I got t to be equal to what then? 4. That means at time, what is that? The 4th hour afternoon? Right? So that would be what, 4 p.m. then? So then now how do we justify that? Well, we're on a closed domain only from 0 to what? So we'd say that a prime at t is greater than 0 for 0 to what? 4. And a prime at t is less than 0 for what? 4 to what? 12. So the maximum is at what? T equals 4 what? Hours. And if we wanted the y value, we're just asking for the t, we put that back in the original function. And number 2, the rate at which concert tickets were sold. Now underline rate. This is a rate function now. This is the rate at which concert tickets are being sold from 0 to 9 hours. T is measured in hours and is modeled by the function r at t. So r at t equals 555t times e to the negative t over 2 power in tickets per hour. This is a rate function. At what time was the rate at which the concert tickets sold is a maximum? At what time is the rate at which the tickets are being sold is a maximum? So what do we want to maximize then? We want to maximize what? Which means we need to take its what? So that would be a product rule if we didn't realize it. But we're going to use our 83 for this. So we're going to put this function in y1. And we're going to do 555 x times second e to the negative x divided by 2, close it. And I'm going to turn that off, and I'm going to go to y2, where I will have entered math 8, the derivative of y1 comma x. So I already have that in mind. I'm on a closed domain from 0 to 9, so I'll change my window and graph it. And hopefully I'll only have one sign change for that derivative. And I do, don't I? Yes? So I need to calculate the 0, second calculate. Takes a little bit. And I think it comes out to be 2. Second calculate 2 for 0. So I'm just going to hit 1, enter, and then 3, enter, and then cursor on top. And I get t to be equal to what here? Anybody get it yet? Yes. So t is in 2 hours. So how do we argue this? Justify. There's that infamous question again. The explanation part, justify. So we have one sign change for r prime. So we can say that r prime at t is greater than 0. For 0 to 2, and r prime at t is less than 0 for 2 to 9. So at t equals 2 hours is the maximum, is the time at which the rate of tickets sold is a maximum. It's just the time at which the rate the tickets are being sold is a maximum. Okay? You understand there that we're maximizing that? And the units of this derivative, guys, the derivative of r prime, the units of r prime, This is r. We're maximizing RT. So we're taking its derivative, which is r prime, and its units would be what? Tickets per hour per hour. Because r is measured in what? Tickets per hour. And then t is measured in what? Hours. So it's actually tickets per hour what? Squared. Okay, go to number 3. Find the point P on the curve y squared equals 2x closest to the point 1, 4. Okay, so let's underline that equation a little different. It's a y squared, so it's a sideways parabola. When you have the y squared, it's a sideways parabola. So y squared equals 2x, and we're talking about closest to the point what? Okay, 1, 4. Yes? Okay, so then, here's what this looks like. When the y is squared, when x is 0, y is 0. And when x is, say, 2, y squared equals what? 4. So over 1, 2, up 2, and then down 2. It's a sideways looking parabola like that. And we're talking about what point along this curve, let's call it xy, is closest to the point 1, 4. Over 1, up 4. So what point along here, this is the point P if you want to call it 1, 4, what point along this curve will get me closest to the point 1, 4? So what concept is this? It's the concept of distance. We're talking about what point along this curve will put me closest to the point 1, 4. Okay, so what point along here puts me closest to that? So what you have to get in these is you have to get the function you're going to optimize. That means maximize or minimize. In the previous 2 examples, I gave you the function that you are maximizing. Now you've got to come up with it. Well, you're going to minimize the distance between the 2. So you need distance. What's the distance between 2 points? It's the square root of what? What is this? This is an xy. The change in the x is squared. So that's going to be what here? 1 minus what? X squared, correct? Plus the change in the what? And that's 4 minus y squared, correct? Yes, everyone? Okay, because I'm doing this one over from the previous example I'd written there. But to get the point, I need distance. I didn't have that because that's what I believe here, minimizing. Closest means the minimum distance between those 2. So this is the one I want to minimize, which means that's the one I need to take the what of? The derivative. Now, what's not good about that? We've got an x and a y. We like to try and convert it in terms of one variable if we can. We do know something. We do know that y squared equals what? So I can solve that for x, which would be a lot easier, and x equals y squared over what? So then I'm going to have it to become the square root of 1 minus x squared plus 4 minus y squared over 2 what? Squared, right?
Should be percentage for x.
What happened?
So then what?
It should be for x, thank you. So this would be what? Y squared, right guys? And this would be then what? Y squared over what? 2 squared, yes, thank you.
That just means normal y.
What?
Yeah, 4 minus y squared squared.
Oh, it should be 4 minus y, thanks. Okay, so we're good? Okay, it's all right. And we could, the other way would be too hard because we have to do it with the plus or minus the square root. So now look at this. To take that derivative would be very messy. We'd have to make this the 1/2 power, drop it down, decrease it by 1, and times it by the derivative of the inside. When really, think about it. Instead of minimizing the square root, just minimize the inside, because when you minimize the inside, that is this, you're going to minimize the square root. So my point is, you don't need to do that. You just square both sides and just work with this piece. This is what I'm going to minimize. But I have to make sure I did have everything converted in there, so I'm okay. And I think for me, what I'm going to use is, I'm going to use some algebra instead of maybe, I don't know, I guess we could do the chain rule here. That's not too bad, is it? So the distance squared would be drop the power down, repeat the inside, times it by the derivative of the inside, which would be negative 2y over 2, or just what there, everyone? Negative y. Plus 2 times 4 minus y to the first times what? This is where I have to be a little careful with my board space here. Do you understand why I'm only focusing on the inside? Because when you minimize the inside, you are minimizing the square root. So why make things more complicated? Alright, I need some more room. That's the only hard part about things up here. So I'm going to clean this up and make this negative 2y, just put this in front, negative 2y plus, what is that? Well, these will drop out, and that's going to give me plus y what then? Plus y cubed, right? And now this will become a minus what? 8 plus what? Yes, not looking too bad. And set that derivative equal to what? And we're getting those critical numbers. So we drop these out. Y cubed equals 8. And what does y equal, everyone? Well, we need a number line test. So we're not in a closed domain. So y prime, if I pick 1 and put it into my derivative, which is down here, if I pick 1, I'm going to pick up a negative, because this will go here. So I'm going to get a negative, and if I pick, say, 3, I'll get a positive. So I have a minimum at y equals what, everyone? 2. And now, if y is 2, what's x? Just plug it back here. And I think x comes out to be 2 as well, doesn't it? So if y is 2, we get that to become squared. Divide by 2, and what's x then? So the answer to the question is the point 2, 2 along this curve, which is here, will get us closest to the point 1, 4. Sometimes they're not always that nice, but that one came out to be that way. All right, let's go on to the next one, number 4. Okay, so I need your attention here on these, okay? Make some side notes here for number 4. Okay. All right, so in these problems, we're going to deal with volume and surface area. Volume and surface area. So just look up here. This is a rectangular prism with a square base, if you will. Yes? So you might want to draw that. You need these pictures handy. That's a rectangular solid with a square base, which means the sides are all the what? The bottom is all the what? Same. So that's your x by x. The bases are the same, the square base. The height is not necessarily the same, so that's y high. The volume of this box is length times width times height, which is x squared times what? That's the volume of that. So just know that, guys, okay? Yes? Surface area of that box is the sum of all the areas. So the bottom area is x squared. But that's the same as the top. So that's going to be what? And then the faces along the side, it's each x times y. Each of these has an area of xy. But there are how many of those? So that's 4xy. So there you have it. You have the surface area of the box, you have the volume of the box. In some of these problems, it's an open top. The open top won't affect the volume, But it's going to change the surface area to being just what? X squared. You got that? Do you see the difference? Don't confuse volume and area, okay? So be careful. So in this example number 4, the rectangular open box has a square base and a volume of 256 cubic inches. So I'm going to set this equal to 256. What dimensions minimize the amount of cardboard needed to make the box? Well, this is what I'm going to minimize, is the surface area. I'm minimizing surface area. This is the one I need to take the what of. Do we understand that? We have 2 unknowns. We need how many equations then? 2. In this one then, we're going to solve, I think it would be easier to solve for y, substitute in, and then take its derivative. We sometimes call this equation the constraints, meaning we are being held to a volume of 256 cubic inches. And then we want, given this scenario, given those constraints, what dimensions would produce the minimum amount of material needed to make the box? Well, when you cover, that's area. When you fill, that's volume. And when you go around, that's perimeter. Perimeter's around, area you cover, volume you fill. So I need to minimize this. I'm going to get rid of that y and replace it with what? Well, y equals 256 over what? Over what? X squared, correct? And you can call it whatever you want. SA, that's surface area. Reduce it. This becomes a 1, that becomes an x. So we get x squared plus, and you can use your 83s. 4 times 256 is 1,024 over what? But this is the one I'm going to minimize, which means that's the one I have to take the what of? The derivative. I'm going to use algebra first and make this x squared plus 1,024x to the what? Now I'll take its derivative to get 2x minus 1,024x to the what? Negative second equals what? Yes? Now I'm going to do what here? Get rid of this, I have no room, so I'm going to make this what? 2x minus 1,024 over what? Get a common. So put this over, times this by x squared over x squared. And then I'm going to get 2x cubed minus 1,024 equals s prime all over x squared. If I set the bottom equal to 0, I can't have a 0 dimension. So I'm only going to set the top equal to 0. That's a very important step in AP. It shows us you're considering the critical numbers. Add the 1,024 to both sides. Divide by 2. And when we divide that by 2, what do we get there? X cubed equals what? And then I take the cube root, x comes out to be what there? 8. So x is 8. But you got to do what kind of test? So this would be s prime. If I pick a dimension, say, of 6, not too far away, I'm really going to get a negative out of that derivative. And if I pick, say, 10, I'll get a positive. So how many sign changes do I have exactly there? 1. So there's a minimum at x equals what? 8. What does y equal? Replace this with 8 squared is 60 what? And y equals, I believe, 4. So it's an 8 by 8 by 4 box. Those would be the dimensions to give that. So listen here, guys. Whether we're talking about volume, area, perimeter, the idea, or distance, the idea has to be clear. Is that you have to recognize first, what function are you optimizing? That means which one are you maximizing or minimizing? You've got to get that function. And then you may have to use the other additional information, like in this one, knowing the volume was 200 what? Where I was able to solve this for what? Y, and put this back in the other equation to take its derivative and hope for one sign change. Okay, go to number 5. Now in number 5, we're going to talk about cylinders. So in this one, we want the radius and height of a cylindrical soda can with a volume to be 354 cubic centimeters that minimize the surface area. So we've got our cylindrical soda can. Oh, I can do a little better. So there it is. We want the radius and the height that will minimize the surface area. So again, we're talking volume and area. The volume of a cylinder, right circular cylinder, is pi r squared times h. Did you ever realize that volume is equivalent to the area of the base times the height? The area of the base is a circle. That's pi r squared. Its height is h. Just like with a rectangular prism. You know, if you don't know, if this is a x times y times whatever, w. The base is y times w and the height is, say, x. So it's the area of the base times the height. The surface area is the total area. So the areas of the top and bottom are pi r squared. So two of them make what? 2 pi r squared. And we call this the body of the cylinder, this piece of the soda can. That is 4 pi, I'm thinking it's 2 pi RH. 2 pi RH. Okay? 2 pi RH. Thinking of the sphere. Got it? 2 pi RH and 2 pi R what? Now is this an open top or no? It doesn't say that, does it? So it's not an open top, is it? If it were an open top, it's only going to be how many of these? So if it's closed, it's what? Okay, so this is the one we want to, I believe, what? Minimize? So what is the volume? The volume is what? What would I solve that for, gang? R or H? So H equals 354 over what? Yep, and where does that have to go now? Into here. So these are a little messy, but they're not bad. You just got to clean them up before you proceed sometimes. Okay? And I'm just going to put that in for H. And then what happens is the pi's divide out here, and then one of these r's will divide out with one of those. So if I multiply that, I get the surface area cleaned up to be 2 pi r squared plus 708 all over what? And that's the one I've got to take the what of. And I didn't even get a derivative yet. So I'm going to make this r to the what? So S prime would be 4 pi r minus 708 r to the what? Yes. Drop it down, so it'd be 4 pi r minus 708 over what? Put this over that, get a common denominator. So it's going to be 4 pi r cubed minus 708 over r squared equals what? 0, right? And I'm going to add 708 and divide by 4 pi, take the cube root, and r is the cube root of 708 over 4 pi. Now, to get a number for that, take your 83s out and type that in. Second square root, 708 divided by parentheses 4 pi. Oh, is it cube root? Jeez, yeah, cube root, sorry. So you need to back up then. Here's what you can do. Hit parentheses, open parentheses, 708 divided by, parentheses again, 4 pi, close it, caret, to the 1 divided by 3 power. And what's that decimal about? Good. So that gives you an idea as of what to pick then. So that is about 3.83, what? 3.833, I think I got. Okay, so then this is S prime, call it. If you pick 2, put it into your derivative, you're clearly going to get what sign out of that? And if you pick, say, 5, you'll get a positive. So where's the minimum at? When r equals the what? Cube root of 708 over what? And where will we put that at to find h? Right there. We'll find h by putting that back in. That's just easy algebra from there. Okay, flip the page over to number 6. A gardener wants to enclose 600 meters squared. Meters squared is what? Area of land in a rectangular plot, and divides it into 2 plots with the fence parallel to one side. What dimensions will minimize the least amount of fencing required? Can you draw a picture, guys? Can you draw a picture of a rectangular plot? Right here. We know its area, and we want fencing to divide it into 2 equal parts, parallel to the other sides. So the fencing is going all the way around, like that. So I can call this dimension x, this dimension y. And the area of this plot, which is x times y, is known to be what? 600 meters squared. That's a constraint. We're confined to 600 meters squared, correct? All right, so then what's our dimensions going to be so we have the least amount of fencing to use, right? So what is that? Is that perimeter, area, or volume? Perimeter. So I'll call this y, this is fencing, this gets fencing, this gets fencing, and this is x, that gets fencing. You don't have to call this a half x and a half x, because that just adds to give you x. So now I can say that 3y plus 2x is my perimeter. This is the one I want to what? Minimize. So that means I got to take the first equation and solve it for what? Y or what? So I'll solve it for y and get 600 over what? So I'll get 3 times 600 over x plus 2x equals p. That's 1800 over x plus 2x equals p. Rewrite it as 1800 x to the negative first plus 2x equals p. The derivative would be p prime negative 1800 x to the negative second plus 2. Set that equal to what then, guys? 0, but I'll get a common denominator. So then I'm going to have negative 1800 over what? X squared, correct? Plus 2. Put this over what? Times this by x squared over what? So now I'm going to have 2x squared minus 1800 equals 0. 2x squared equals 1800. X squared equals 900. And x equals 30 as the square root of that. So then I need a number line test on that. So 30, this is p prime. Where will I put the 30 back into my derivative? This is over the bottom squared, which I know can't be a critical number. So if I pick 20, that's 400. 800, I clearly get a negative. If I pick 40, I'll get, what is that? 16, correct? So it's clearly going to be what then? Positive. So there's going to be a min at x equals 30. What's the other dimension? Just take 30, right? Where was my y equation? I erased it, didn't I? So y was 600 over what? X, right? So x is what? And then I'll get 20 then. So it looks to be the dimension to be 30 meters by what? And that is an area of what? 600. Okay, turn your chairs that way to go over the homework there. Tomorrow we'll resume the quizzes. I'll be here during, like I said, of course, all 10 periods and morning. It is? Yeah, okay. So, okay, so here we go. Number one, as quickly as I can get through, at least to learn the answers. Tomorrow we're starting with your rates. Okay, so here we go. Number one, this is, right here, x plus y equals 20. I'm going to, I think one of the numbers